Hello, students. This video is going to cover Chapter 3, which is Kinematics in 2 dimensions. All right, so we're going to find out that in Kinematics in 2 dimensions, we're not going to have to find anything new. Back in Chapter 2, we defined all the variables that are going to come to play for a theory of kinematics. Now, in Chapter 2, we're restricted to just one dimension. In Chapter 3, we're actually going to release that restriction and we'll actually work in 2 dimensions. So we'll actually see vectors more depicted as they usually are. So in general, a vector that we normally think of, we can think of it better written in 2 dimensions. So we would have our x and y components as usual, plus x plus y minus y. And we would draw a vector out, like I'll just draw one here in the first quadrant. As usual, maybe I'll call it R with a hat. Again, it's some vector that has some component in the x direction, some component in the y direction, as usual. So what would I do? I would draw down the vertical. I know that the y-axis and the x-axis are perpendicular to one another because the Cartesian system is orthogonal. And so this forms a right triangle. And so I can think of there being a x component r sub x along the bottom leg of this triangle and a y component r sub y. So our vectors look more like your typical vectors. And they're easier to show independently, as opposed to being drawn on top of one another. All right, so this is your typical, just a typical vector. It has, and I would say that this has an angle theta. We'll say theta, angle theta, and so again, I can express the components, and we've done this in last couple of lectures. But I can express r sub x as r, the magnitude r. Now, basically, I imagine that if I take the hat off, this hypotenuse has a magnitude of r, which is just a number, just a scalar, times, again, this is the adjacent leg, so it'll be cosine of theta, and r sub y would likewise be r times the sine of theta. So again, this is much more or less a review of what we've talked about in the last couple of chapters. But now we can actually employ these vectors in their two-dimensional form in this particular chapter. All right, so that's what we're going to do. There's not really any new major concepts. We're going to see. We're going to drive a couple other equations and talk about it. We're going to talk about probably one other concept called relative velocity. But generally speaking, there's going to be no new major kinematic concepts. All right, we're just going to apply it in a two-dimensional sense. All right, so the first topic that one generally covers in two-dimensional kinematics is what's called projectile motion. All right, so projectile motion is the motion that you see if you imagine a pirate ship shooting a cannonball, or let's say a baseball player hitting a fly ball. Essentially, what it looks like, and I'm going to try to draw. I'm going to try to draw a fairly large drawing so I have some detail that I want to share. So let's just kind of imagine that I have y-axis and an x-axis. Now I'm just going to draw more like a kind of a first quadrant, kind of a picture. Go further out than that. And let's kind of look at what a projectile motion would look like. It's essentially the shape of a parabola. This is from our experience. There's going to be an initial velocity vector. So let's just kind of draw it out here. Let's draw a parabola as best I can. Let's see here. How does that look? It's not too bad. All right, so that's what the motion of the ball is going to look like. Again, from our experience, we know that we think of this as a cannonball shooting a pirate ship shooting a cannon. And the cannon's going to come up, and it's going to follow a parabolic path and hit its target. Or, for instance, it might be a baseball player hitting a baseball, and the ball goes up and it comes back down and it gets caught by an outfielder. So that's the kind of motion that we know exists. We see that from our own experience. Now, how do we analyze this motion? Well, first of all, we need to understand something, that there's actually going to be independent motion going in each coordinate. There's going to be independent motion in the y coordinate and independent motion in the x coordinate. So in the y coordinate, there actually is acceleration because of gravity. So there will be independent motion. In the x and y coordinates. Okay? In the y coordinate, so I'm not blocking anything here. In the y coordinate, we have free fall. We talked about free fall in chapter 2. And we have free fall because gravity only acts in the y direction. In the x coordinate, okay, we have constant velocity motion. So I would say constant v, constant velocity motion. Okay? And so, because there is nothing to accelerate the projectile in the y direction, in the x direction. In the y direction, there's gravity. Gravity causes there to be an acceleration. The acceleration is due to gravity. We're assuming there's no air resistance. So gravity will operate only in the y coordinate. There's no acceleration. There's no reason for the body to accelerate along the x coordinate. So the x coordinate is just going to experience constant velocity motion. So we have two independent types of motion that are going to be occurring in this projectile motion scenario. Okay, and so this is actually free fall. I can say off the camera here, free fall. There you are. Okay, so all right, so let me erase the words here and let's start analyzing this picture. All right, so two types of motion. And I'm still talking about projectile motion. Okay, so free fall. Let's just kind of talk about the y component first. So free fall is going to happen. Is going to look like what? Well, first of all, whatever we're talking about here, for instance, maybe it's a cannonball being shot, or maybe a gun being shot at a certain angle, or maybe it's a baseball being hit. There's going to be an initial velocity vector. And so we can refer to this as V naught, initial velocity vector. There will be an initial angle in which this projectile will be launched, and that'll be a theta naught, angle theta naught, right? And so that's the initial angle. Now we can put the two components. We can essentially analyze this vector in terms of two components. So we can draw a perpendicular and a right angle. We know that, for instance, that because the Cartesian system, the coordinates are at right angles because the system is orthogonal. And so we know that we can break this up into essentially a v sub, well, I'll write it over here, a v sub y, or v naught sub y, okay, and a v naught sub x. Okay, so v naught will be composed of so much v in the x direction, so much v in the y direction. So v naught sub x and v naught sub y. Okay, and we know that v naught sub x is v naught cosine of theta naught, and v naught sub y is v naught sine of theta naught. All right, so again, everything we learned about before in vectors can be applied here. So this is this initial velocity vector. Now, let's kind of we'll worry about the mathematics in a moment, but we know that we can break these into components. So let's just worry about the y component first. Okay, so we know that if the y component is experiencing free fall, then the largest velocity vector that the y component will experience will be the initial velocity vector. As the projectile rises up toward its pinnacle, it's actually the vertical component is going to get smaller and smaller. We saw this last time. So let me pick a few points. Let's say I'll pick a point over here. Now we see the velocity vector is, this large initially. Well, it's going to get smaller. So I'll try to do it kind of qualitatively here. So that's the v sub y a little bit later. I'll pick a point even later. Nose is getting shorter, v sub y, and it's getting really stubby now, v sub y, and then at the pinnacle there's no v sub y component. And then we fully would expect there to be a symmetry in the motion. So as the body is falling, v sub y will get progressively larger. So initially it's not very big. As we move along, it gets larger. Later on, still larger. And we expect everything to be more or less symmetrical. By the time it gets down, it hits the ground, the v sub y component should be as large as the initial v sub y component. So it should be symmetrical. So v sub y, the y component is experiencing free fall. Now, the x component, on the other hand, experiences constant velocity of motion. That means that it does not experience acceleration. So v naught sub x is going to be the x component every single point in the motion. All right, so if I look later on, I have v naught sub x, same size. Later on, v naught sub x. This is going to look a little bit complicated in this drawing, so I have v naught sub x, v naught sub x, v naught sub x, v naught sub x, and finally, I'll just write it this way, v naught sub x. All right, so all along, the x component of velocity does not change at all. It is the same. The motion in the x direction is constant, does not change at all. So the motion in the y direction is free fall. So you have two independent motions. The y component motion is free fall. The x component motion is constant velocity. The two, when you combine the two together, when you combine free fall and the object moving at constant velocity at the same time, you get this parabolic motion. All right, so again, that's the motion that you get, this trajectory, when you have these two independent motions occurring at the same time. These two motions are independent. Now, how do I analyze this mathematically? All right, so I'm going to erase my drawing here, and let's talk about the mathematics involved in projectile motion. We kind of understand qualitatively how this works. So in the y coordinate, what equations apply? So in the y coordinate, we would expect to see free fall, and so all right, let me see if this pen is better. All right. Here we go. Remember, the y coordinate is going to experience free fall. So this is a one-dimensional problem, just like we talked about in chapter 2. The y coordinate is going to experience free fall, so we just literally write down the free fall equation. All right, so we had y minus y naught is v naught plus v, and actually let me be more specific here. V naught sub y plus v sub y over 2 times the time. So this was y equals y naught, y minus y naught equals v bar t. But let's be specific about this. These are velocities in the y direction. You know, we have to be specific. We have to be specific because we have to specify, which direction, what coordinate, because there's going to be velocities in the y direction and the x direction. So these are y component velocities. All right, so that's one of our kinematic equations for constant acceleration. Another one that applies is v sub y is v naught sub y minus gt. Again, gravity only applies in the y direction. We're assuming the y coordinate is positive up. All right, another equation we have is y minus y naught is v naught sub y t minus 1/2 gt squared. And then we had the fourth kinematic equation, and that was v sub y squared equals v naught sub y squared minus 2g times y minus y naught. Okay, these are the equations that govern free fall. These are the equations that you use to discuss free fall, and again, these equations only apply to y component, the motion in the y component, because again, gravity only acts in the y direction. In the x direction, so the x coordinate is very simple. The x coordinate is going to be literally an algebra 1 equation. So it's going to be basically x minus x naught equals v naught sub x times t. Basically, it's your typical d equals vt equation. All right, you see from algebra 1. That's all that's going on. This distance is velocity times time. All right, and then we know specifically that v naught sub x is v naught cosine theta naught, and also we know that v naught sub y is v naught sine of theta naught. Again, these are constants. These v naught sub x and v naught sub y are determined at the beginning of motion, at the launch. So theta naught is the initial angle, the initial launch angle, and v naught is initial launch or muzzle velocity, if you will, or muzzle speed, I guess. So these are the constant and initial velocity variable or initial velocity. These are the two components, and so this is how it applies. You only see the x component of velocity, the initial velocity, all throughout the entire problem. That's all you see, and so essentially, there is only one equation that applies in the x coordinate, where the kinematic equation is applying the y coordinate. Now, these two sets of equations apply simultaneously. They are totally independent, except they share one variable, and that is the time. So essentially, one of the coordinates ends up acting as a stopwatch, if you will. I mean, for instance, if a body hits the ground, that means that the y motion is done. That means the problem is done. So that means that however long it took for the body to rise and fall and hit the ground, well, basically the time is being governed by this motion. And so, because when time's up for the y component, time's up simultaneously for the x component. Or it may very well be that the x component, maybe the object hits a brick wall first, and maybe it could still fall some more. But the fact is, it hit a brick wall or maybe it's stuck to the wall, and now the motion's over. Now the problem's over. So one of the two motions is going to dictate that the entire problem is over. Yet they work independently, but like I say, the only variable they have in common is the time. All right, and so that's really all that's to this. I mean, essentially, I'm going to work through some projectile motion problems, but there's no more theory to talk about. It is free fall in the y component and just constant velocity motion in the x component. That's it. All right, so there's really nothing else to talk about theoretically. We've defined everything. We've talked about vectors, and we have talked about kinematics. All the kinematics we need to do this problem. All right, I do want to discuss a particular equation that I think is very important. So make note of these equations. I'm going to use a couple of them in a moment. I'm going to make another derivation. All right, and so I'm going to erase the board. And so again, these are all the equations we're going to apply, and we'll work some problems out to kind of see these in action. Now, I'm going to kind of derive something that's pretty cool, and this is called the range equation. So we're going to find out that all I really need to know is the initial velocity vector, and I can determine how far a projectile will go in the x direction. So we call that the range equation. So for instance, if you know an enemy ship is a certain distance away, you're going to the muzzle velocity of your cannon. All you have to do is essentially, if you know that distance that you want to strike your target, then what this distance can tell you is that you can basically understand that you can dictate what the range is by basically controlling the angle of the initial velocity vector. And so once we know v naught and theta naught, we can determine the range. So it's a very neat equation. Essentially you can determine how far in the x direction your projectile is going to go by knowing very little. I mean, essentially all you have to really know about is your initial velocity vector. And so how does this range equation work? All right, and so we know that the only equation that operates in the x direction is x minus x naught is v naught sub x times t. Or specifically, and we'll define, for the purpose of this application, we'll define what's called the range. And that's basically x minus x naught. That's the displacement, the horizontal displacement. We just call it r for the range for this particular application. And v naught sub x is v naught cosine of theta naught, and then that's multiplied by t. Okay. All right, so essentially what we get out of here is that the range is V naught cosine of theta naught multiplied by t. All right, so I want to kind of hold on to this equation, and I'm going to kind of write it up here. Essentially, I have very limited whiteboard space, and so I'm going to write the equation off to the side here. So the range is, again, V naught cosine of theta naught multiplied by the time. Okay, so I'm going to put that to the side, erase this, and that's really the only equation I have in the x direction. There's not much to go with in the x direction. Now, in the y direction, I want to employ the following equation, and so I want to say that v sub y is equal to v naught sub y. And then what I really want to do is I want to discuss the upward motion. And I'm going to use symmetry to say that the downward motion is going to be exactly like the upward motion. And I want to try to figure out how long it's going to take for the projectile to rise to its pinnacle. All right. And so essentially I'm going to say that v sub y is v naught sub y minus g t sub up. Again, this is essentially the motion of projectile, or we'll say the y component motion of projectile. From its launch to its maximum heights. Now, we know that at the maximum height, so at the maximum height, v sub y is 0. So again, when an object that's in free fall reaches its maximum or pinnacle height, its velocity is 0. So again, we're just talking about the y component here. So for the y component motion, which is free fall, the pinnacle velocity will be 0. And so I want to try to find out how long that takes. So I'm going to make this equal to 0, and so essentially what I now have is that this becomes 0, and I can essentially add g times t up on the other side. I essentially get g times t sub up equals v naught sub y. All right, and then I'll divide both sides by g, and I'll say that t sub up is v naught. Now, what's v naught sub y? That's v naught sine of theta naught, and look back at your notes, divided by g. Okay, so that's how long it's going to take for the projectile to rise. Now, by symmetry, total time, we'll say time TOT, is going to be the time to go up plus the time to go down. Okay, so there's going to be a certain amount of time for the projectile to rise and a certain amount of time for it to fall. Now, we make the statement here. I'm going to erase a little bit of this. We're going to make a statement that by symmetry, well, actually, we know the total time is time up plus time down, but by symmetry, we say that we expect that the time for the projectile to rise is the same as the time for the projectile to fall. there's no reason for me to believe otherwise. And so what that basically means is that T total is going to be time T up, and then T down is the same as T up, so I can essentially write this as 2 times T up. Since we know that T down is the same as T up, we can substitute for T up. And we know what T up is B naught sine theta naught over divided by G. So this becomes, the total time becomes 2 B naught sine of theta naught all divided by G. That is the total time. All right, so that's the time for the entire motion. All right, so what I can write here is this is the, and we can just call this, again, this range is the same as the total time. Right, this is the total time of flight. So the range tells you how far does the projectile go. So clearly, when it reaches its maximum range, it will have expanded its total time. All right. So again, how far the projectile goes, essentially, it's like you go from the launch position all the way out into the final landing spot, and how far along X it goes from launch to landing. That's your R. So again, the R will occur when the total time has elapsed. All right. And so what I can now do is I now know that the total time, as I just got done seeing here, the total time, let me erase some stuff here. So the total time is 2 B naught over G sine of theta naught. Okay, so again, that's what we just got done deriving. And I'm going to plug this I'm going to substitute into the total time variable in the range equation. So I'm going to eliminate this left equation, and I'm going to substitute it into the right equation. And so now the range becomes B naught cosine of theta naught multiplied by, and then the total time is going to be 2 B naught over G sine of theta naught. Right? All I've done is I've derived the total time it'll take for the projectile to go all the way up and then all the way back down. And that's going to equal the total time for the projectile to go its entire maximum range. All right. And so you combine the two times, and we essentially will now combine like terms here. All right. So we're going to essentially take the V naught squareds and put them together. So I have V naught squared over G. I'm just going to rearrange this a little bit. See if I'm still in the camera. All right. And then what I'm going to do is I'm going to rewrite the rest of it in kind of a suggestive way. The rest of it I'm going to say is multiplied by 2 sine of theta naught times the cosine of theta naught. All right, so I'm just pulling the V naughts together and the G. Now, if we go back to trigonometric identity, we find out that the sine of 2 theta naught is equal to 2 sine theta naught cosine theta naught. This is called a double angle identity. So if you look this up in among your trigonometric identities, you find out that sine of 2 theta naught or sine of 2 theta is 2 times the sine of theta times the cosine of theta. So that's a double angle identity. So what that means that I can do is I can substitute what I see 2 sine theta naught cosine theta naught. I can substitute that for this double angle. And so finally, if I do that, I can finally write the range equation. And that is that the range is V naught squared over G sine of 2 theta naught. That is a range equation. So I'm going to erase the rest of this. Now, what does this mean? Well, this means that, I know what gravity is all the time if I'm on the Earth. So I really just have to know. So essentially, depending upon how if I know my muzzle velocity, essentially how I aim the cannon will determine how far the range is. So depending upon how I aim the cannon, I will determine what the range is. So if I aim the cannon a little higher, I'll have more maybe a shallow range. If I aim a little lower, maybe shallow. Essentially, all I really have to do is know V naught and theta naught. Or, putting these together, V naught the vector. So V naught vector corresponds to the scalar V naught and the angle, right? And so if I know the initial velocity vector, then I will automatically know the range, because I will know what the magnitude of that velocity vector is, and I know the angle of that velocity vector. And so all I have to know is the initial velocity vector, and I can determine the range of the projectile. And so it's a very useful equation. Now, one question you might ask is, well, what might be the maximum range? So let me ask this question. What might be the maximum range? I mean, how do I determine that? I'll call that R max. Okay, what's the maximum range? Well, V naught is a characteristic of your gun or your cannon. You usually have an idea of what your muzzle velocity is. Okay, that's usually a constant of the problem. That's usually a characteristic of whatever gun you're shooting or cannon you're shooting. And so that's usually a constant of the problem. G is gravity. And so the only variable you really have is how you aim the gun, how you aim the cannon. And so we really want to try to get a maximum value of R, you have to get a maximum value of this sine function. And so the question then would be, what is that maximum value? Well, the sine function maximizes at 1. So the maximum value of the sine function is 1. Well, the sine of what is 1? Well, the sine of 90 degrees is 1. And so 90 degrees, if you can have your argument be 90 degrees, then you will achieve an R max. So how do you do that? Well, you say that I know I have this double angle. So 2 times theta naught is 90 degrees, or theta naught is 45 degrees. So R max occurs when your launch angle is 45 degrees. All right? And so let's write this down. So the maximum value of R, the maximum range, occurs for a launch angle of theta naught equals 45 degrees. And then R max would then become, well, in that case, if this angle is 45 degrees, 2 times 45 degrees inside the argument is 90 degrees. The sine of 90 degrees is 1. So your sine function maximizes out at 1. So your R max then becomes simply V naught squared divided by G, because your sine function has maximized to 1. So again, that is the maximum value. The maximum range of your cannon occurs at a 45 degree angle. Okay, and so again, this is the range equation. We'll see it again. We'll use it, and this would be what your maximum, your R max would be. So we're able to combine the equations for projectile motion. Again, the equations that in the y freefall equations in the y component, and the single constant velocity equation in the x component. We're able to combine those two and get a and essentially get a range equation. All right. So let me see here. Let me work. All right. So let me work a few problems. All right. So all right, so I had to kind of, usually I like to do open stacks, but I had to kind of go to Cutnell and Johnson for some of these. I didn't see very good problems in open stacks for once. So let me look at, so again, Cutnell and Johnson is your actual bona fide textbook. So when I do a Cutnell Johnson problem, I'll say CJ for Cutnell Johnson, as opposed to OS for OpenStax. All right, so let's do Cutnell Johnson 3.14. So again, we're in chapter 3. So chapter 3 is where we are. We'd actually be chapter 3 in OpenStax as well. They're oftentimes they have the same chapter numbers. All right, so Cutnell Johnson 3.14 says, is as a tennis ball is struck, it departs from the racket horizontally. With a speed of 28.0 meters per second. The ball hits the court. At a horizontal distance of 19.6 meters. All right. From the racket. How far above the court is a tennis ball when it leaves the racket? All right, so again, the problem states, as a tennis ball is struck, it departs from the racket horizontally with a speed of 28.0 meters per second. The ball hits the court at a horizontal distance of 19.6 meters from the racket. How far above the court is the tennis ball when it leaves the racket? All right, so you have a tennis ball that's at some sort of height above the court. I'm sorry, above the court, which is what we're asking. It gets struck with an initial horizontal, totally horizontal velocity, no vertical component. And essentially, what's going to happen is going to, as any projectile, it'll undergo free fall in the y direction, and at the same time, horizontal constant velocity in the horizontal direction until it strikes the court. And then once it strikes the court, once the free fall, once the y direction, once the y component free fall is done, the whole problem is done. All right, and so essentially we that's the problem that we have. I mean, it's kind of the age-old problem of the rifle shot. You know, there's a interesting experiment one can perform where if you aim a rifle horizontally and at the same time you drop a bullet, the two bullets will strike the ground at the same time. So if you have an experiment where you shoot the rifle horizontally, so you have a rifle, you shoot it horizontally, at the same time you drop a bullet, the bullet that's just dropped from free fall will strike the ground at the same time the bullet is shot out of the rifle. Now, sometimes that surprises people, but again, if the bullet coming from the rifle, it may have a crazy large horizontal component of velocity, but again, the free fall for the bullet that just gets dropped and the bullet that gets shot will be the same. And so they will hit the ground at the same time. So this is kind of the same kind of problem with the tennis ball. And so we see that, let's get some information off of this. So we know that the tennis ball departs with a horizontal speed of 28 meters per second. Okay, we know that, it's v naught sub x. And it's going to strike the court at a horizontal distance of 19.6 meters. That's x minus x naught. All right, so this is what I can read up there. I have to erase this to do the problem. So let's erase this and work out the problem. All right, so what I know, again, is that v naught sub x is 28 meters per second. So again, initially, the entire velocity vector is actually horizontal, which means then that v naught sub y is 0. So in the free fall problem, that's corresponding with the horizontal constant velocity motion problem. Free fall particle is essentially as if you dropped the tennis ball toward the ground. There is no initial velocity in the y direction. All right, so what else do we know? Well, we know the x minus x naught, the range in the x direction, that we're being told that's 19.6 meters. What we want to find is y minus y naught, and that is the height above the ground in which the tennis ball, when the tennis ball struck, how high was it above the ground? Basically, how far did the tennis ball fall? So again, there's two motions going on. You know, if the tennis ball, the horizontal motion, there's no fence or something in the path, the tennis ball can hypothetically go forever in the horizontal direction. What stops the problem is when a tennis ball is when the vertical direction, when the tennis ball hits the ground because of the vertical motion. That's what stops the problem. So one of the two motions, as I said before, will stop the problem. In this case, the problem stops when the free fall causes the tennis ball to strike the ground. Okay, so again, two different motions going at the same time. And so what we want to see here is that, okay, well, we have, let's see, what can we do? Well, we essentially know x minus x naught, and we know v naught sub x. And so essentially we have to use one of the equations to kind of figure out when does the problem stop? We don't really have enough information in the y direction, but essentially the x equation, we can actually use that to actually determine the time when the problem stops. All right, so essentially we can write down that the only equation we know in the x direction is x minus x naught is v naught sub x times t. And that's all we know. But however, we do know x minus x naught, we do know that range, and we do know v naught sub x. In fact, v naught sub x is the entire initial velocity, right? And so we can actually use the x equation to figure out how long the problem is going to take. Essentially, how long does a free fall occur? We don't have enough information in the y direction to even know this. So we have to kind of use the x coordinate first to determine, in this particular problem, when does the problem stop. Then we can use that information and apply it to the y-dependent equations, or the y equations, all right? So we have enough information that is to determine when the problem is over. So I'll solve for time. So t is going to be x minus x naught divided by v naught sub x. All right, so we know that information. We know that x minus x naught is 19.6 meters. And v naught sub x, so that's the entire initial velocity of the tennis ball, that's 28 meters per second. And so we find out that the problem takes essentially the tennis ball going at 28 meters per second in the horizontal, the horizontal velocity 28 meters per second. Oh, by the way, that's always going to be the horizontal component of the velocity. Now the velocity vector will actually increase. Why? Because it's initially had 0 vertical component, but by the time the tennis ball hits the ground, it'll have its maximum vertical component, and it'll still, and so there'll be 28 meters, there'll be so much vertical component in the y direction when a velocity when the tennis ball strikes the ground. Combine that with the constant 28 meters per second in the x component, and you'll have an overall larger velocity. You'll have a magnitude that's combined with the x component and the y component. You have a larger magnitude of velocity, but the horizontal component will remain constant throughout the entire problem. All right. So the question is, how long, if a tennis ball is going horizontally at 28 meters per second, how long will it take to go 19.6 meters? That's all we're asking here. And if we do that, we find out that that's going to take 0.70 seconds. So this whole problem is going to take 0.70 seconds. So that's how long it takes a ball that has a horizontal velocity, horizontal component velocity at 28 meters per second to go a range of 19.6 meters. So that's the whole time of the problem. I know what the range is. That means that that's the same amount of time that the problem can take in the vertical component as well. Okay, so this now employs or applies a constraint to my vertical motion. All right, so in the vertical motion, what we want to determine is what y minus y naught is. Well, now we have the time. So now we have a time, and now we have initial velocity. And so we go to our catalog of equations that we talked about last time. And probably the best equation to use would be this one. Y minus y naught equals v naught sub y t. And what I'm going to do is I'm going to employ an upside down y component. So I'm going to employ a y direction in this case, because everything's falling. I'm going to employ that positive y is down. Why? Because all the y direction, the y motion is all down. Everything is falling in the y direction. So why not make life easy and just have an upside down y coordinate system? That's perfectly legitimate to do that. So that means that if that's the case, then I have a plus 1/2 gt squared. Okay? So again, I'm going to have a positive. All of my motion is going to be positive because all I really have is falling in the y direction. All right, and so and pretty much I know everything because I know that v naught sub y is 0. This equation quickly becomes y minus y naught is 1/2 gt squared. And we know t, so this becomes easy. Y minus y naught is 1/2 9.80 meters per second squared times, and we're told it's 0.70 seconds. Let's see, 0.70 seconds. So I stay in the camera here, yep, squared. All right, and if we do that, we find out that the initial height of the tennis ball, y minus y naught, is equal to 2.40 meters. All right, again, what did I do? I mean, I have two types of motions, independent motions that are occurring at the same time for any projectile motion. And so we know that the tennis ball has entirely horizontal velocity. However, it's going to maintain that horizontal velocity in the x direction. The entire problem. It's going to gain more and more velocity in the y direction. So overall, the total velocity vector is going to increase. All right, and so we know that again, it's essentially we have a free fall problem where literally it's the ball is falling from rest in the y direction. All right, we know the horizontal range, and we're asking what the vertical height was. What's the vertical displacement? And so we knew enough information in the horizontal equation to figure out how long the problem takes. We took that information as another piece of information and then went to the y constant velocity kinematic equations and utilized that, and also the information that we know that the initial velocity and the component in the y direction is 0. Combine those together with the appropriately chosen equation to solve for that vertical displacement. Okay, so that's what we did to recap. All right, so now I want to do another problem. All right, and this will also be out of Cutnell and Johnson. Okay, I would like to do Cutnell and Johnson 3.22. Okay, so you own Cutnell and Johnson, but I'll essentially rewrite the problem anyway. So essentially, it says a space vehicle is coasting at a constant velocity. Some of the Cutnell and Johnson problems are long. Of 21.0 meters per second. In the positive y direction. Relative to the space station. Okay, the pilot of the vehicle hang on 1 second. The pilot of the vehicle fires an RCS RCS, they say, stands for Reaction Control System Thruster. okay, which causes it to accelerate. At 0.320 meters per second squared. In the positive x direction. Okay. After 45.0 seconds, the pilot shuts off the RCS thruster. Okay. After the RCS thruster is turned off, find A, the magnitude and B, the direction of the vehicle's velocity relative to the space station. See how much I can fit on here. A long problem statement. Space station. All right. You know, some of these problems in Cutnell and Johnson are very long-winded. So, and then I'll read it, and then it says expressive direction is an angle measured from the positive y direction. Okay, we'll have to remember that. I don't have enough space here. So again, it says a space vehicle is coasting at a constant velocity of 21 meters per second in a y direction. Okay, so it's initially going in a y direction at 21 meters per second and just coasting. Okay. Relative to the space station. All right, so again, we're talking about a space vehicle. Everything is relative to the space station. So there's a space station there that's really allowing us to have some form of reference. Well, we always talk about having a reference frame. Well, the space station, everything is moving relative to the space station. All right, so the space vehicle is moving relative to the space station. The space station forms a reference frame. All right. So 21 meters per second, constant coasting. Now, that's in a y direction. Get a picture here. The pilot of the vehicle fires an RCS thruster, which causes it to accelerate 0.32 meters per second squared in the x direction. So now it's going to start accelerating in the x direction for 45 seconds. The pilot will shut off the thruster. At that point, we want to find out, after the RCS thruster is turned off, find A, the magnitude, and B, the direction of the velocity. All right, relative to the space station, we want to express our angle relative to the y-axis. All right, so what's going on is initially there is no x. So this is almost like a backwards problem, what we normally see. Normally we have acceleration in the y direction and constant velocity in the x direction, right? Like in the last problem. In this problem, the roles are reversed. So we have no acceleration in the y direction. The y direction is the space vehicle is constantly coasting. And in the x direction is where you're getting acceleration. You're getting acceleration for a certain period of time. So when things are over, you're still going to have, when when the RCS thruster gets shut off, you're still going to have that 21 meters per second constant coasting in the y direction. In the x direction, on the other hand, you will start from a velocity v naught sub x of 0, and you will accelerate for a certain amount of time, and you'll end up with a component of v naught sub x. And then your final velocity is going to be that initial v naught sub y velocity, where you're coasting, and the v naught sub x velocity finally, and then you'll combine the two to get the final velocities. That's what's going on in this problem. We want to express this as a velocity relative to the y direction. All right, so a lot of words in this problem, but it's not so bad. So I'm going to erase all this and let's work it out. So you always kind of get an idea of what it is that you're even, draw a picture of what it is you're doing. So we don't have enough room on the whiteboard to draw the picture, so I kind of talked it out. So first thing I'm going to do is draw the picture, of course. All right, so as we're told, the space station forms a reference frame, right? So the space station provides a reference frame for the space vehicle. You have to always have a reference frame when you do a problem. Your velocity with respect to what? So again, you have to always be talking about some sort of a reference frame. Again, as we talked about in our chapter 2 lecture, everything depends on the coordinate system that you lay down. All right. Now, from there, what do we have? Well, we know that this is the y direction. This is the x direction. Okay, there's our orientation. We know that there's always going to be a velocity v naught sub x. I'm sorry, v naught sub y. So v naught sub y is constant. It's going to be constant at, as I said, 21.0 meters per second. Now, initially, there is no v naught sub x. So essentially what's going to happen here is you're going to have basically a parabola that's going to be heading over more toward the x direction. You're going to have more and more x component over this time when the thruster is turned on. So we would see something like this. As soon as the thruster gets turned on, we would see some sort of a parabolic motion. And so all along, initially we don't have any velocity component, and we're going to have a we're going to have an increasing v sub x. So the v sub x is going to increase, and it's going to get larger, all the while v naught sub y is the same. All right, and so the question is, the acceleration that's going on in the x direction, we want to find out what that final velocity is. All right, and so in the x direction, what we have is we know that v naught sub x. So we know that v naught sub x is 0 because initially the space vehicle is entirely coasting in the y direction. Now, we know that the time that the thruster is going to be turned on, we know it's going to be turned on for 45 seconds. That's what we're being told. We would like to find out what the final velocity actually is. And so the equation that we would pick, we're also being told that the acceleration that's going on in the x direction, the acceleration is 0.320 meters per second squared. So we know the acceleration. We know how long the acceleration is going to occur. We know the initial velocity. So we don't know anything at all about the displacement. So a good equation to use would be v sub x is v naught sub x plus a t. Now we're going back to our kinematic equations. We know that v naught sub x is 0. So it's simply going to be that v sub x after 45 seconds is going to be 0.320 meters per second squared times, if I can put this in the camera here, 45 seconds. All right, and so v sub x at the end of the thruster phase, the RCS thruster phase, if you multiply these two numbers together, you get 14.4 meters per second. Okay, so that is going to be the x component of velocity after the thruster phase. Initially, it was 0. Meanwhile, the y component of velocity remains the same. So your final velocity is going to be the constant y component of velocity and the final x component velocity. Okay, so let's take these two pieces of information and finish the problem. We want to find out what the final velocity vector is. All right, and so let's get this. Let's take this information. I just need these two pieces of information, and we'll finish the problem. We're now just going to discuss the velocity vector. So again, I need to conserve my space here. So at the end, we know that we want to have a magnitude and direction of the velocity vector. That's what we're trying to find out. So again, we have y component and an x component. We expect there to be, there's going to be a positive y and a positive x. That's what we expect. So at the end, there's going whatever the velocity vector is going to have a positive y and positive x. There's going to be some sort of vector that's in the first quadrant. We will call this the final velocity v. Okay, so it's going to have a y component. Again, we want the angle with respect to the y axis. That's what the problem asks for. So it specifically requests this angle theta. And so there's going to be v sub y, and v sub y again is that constant coasting v naught sub y. That never changes. The spaceship is going to consistently coast at v naught sub y. What changes is v sub x because of the acceleration. So there's going to be an x component of v sub x. Or was say this one, v sub x. Okay, so let me write this better. All right. So again, after the RCS thruster is fired, and after it's turned off, you're going to have the final velocity is going to be a combination of the constant velocity component in the y direction and the final velocity in a component in the x direction. That combination. So essentially, what I want to now do is figure out what the magnitude and direction of that vector is. That's all that's left. All right. So we're going to practice our vectors. And so how do I find the magnitude? Well, I use the Pythagorean theorem. So again, this is going to have a magnitude of v along the hypotenuse. And so I'll use Pythagorean's theorem. So again, v is going to equal the square root of v sub x squared plus v naught sub y squared. Again, all I did is I employed Pythagorean's theorem. Again, these are three vectors. They're velocity vectors. It doesn't really matter. Any vector operates the same way. It has a magnitude and a direction. So again, every vector, we can do the same arithmetic that we've done all along. So again, every vector has a magnitude and a direction. Different vectors represent different quantities. Velocity vectors, position vectors, displacement vectors, force vectors. It doesn't really matter. They all operate the same way. And so so you determine the magnitude by literally taking Pythagorean's theorem, v squared equals v sub x squared plus v naught sub y squared, and taking the square root of both sides to write this. That is just 2 steps of algebra 1. So v will be, we have v sub x. What did we find out that it was? It was 14.4 meters per second. Quantity squared. And then the coasting velocity is 21 meters per second. That stays constant. And that has to be squared. And you must take the square root of everything. If you do that, you find out that the final velocity is going to actually be 25.5 meters per second. Okay, so that's the final velocity magnitude. And then we want to find out what that angle is. So again, let's be very careful. This is actually a good problem to kind of show you that the tangent is not always y over x, right? So remember, the tangent of theta is the opposite divided by the adjacent. Well, this time, the opposite is actually going to be v sub x, not a y. So it's v sub x now, and your adjacent is v sub y, or v naught sub y. So now we actually have a x over y because of the angle that I'm trying to determine. So theta will then be the inverse tangent of v sub x over v naught sub y. Okay, so we'll plug in some values here. Theta is the inverse tangent. V sub x is at 14.4 meters per second. And v naught sub y is the 21.0 meters per second. So again, the transitional function is unitless because the meters per second cancels out. And so if I do this math, I find the inverse tangent, I'll find out that theta is equal to 34.4 degrees. Oops. All right, so this is a 2 pieces of information. I know the magnitude and the direction. So my final answer is going to be V is equal to 25.5 meters per second at theta equals 34.4 degrees from y-axis. That is my answer. Okay, I think this is a good problem because some of the normal roles were actually reversed. What we normally called x became y and vice versa. All right. All right, so that was Cutnell-Johnson problem 3.22. All right, let's see here. I want to do let's see about 3 more problems. One that's fairly long, and then the other ones are not so bad. All right, so let's do a little bit more work. All right, so that's that problem. All right, so the next problem I'd like to do is Cutnell-Johnson 3.43. Okay. That one says an airplane is flying with a velocity of 240 meters per second. At an angle of 30 degrees with the horizontal. Okay, and it says as shown in the drawing. I'll repeat the drawing here in a minute. When the altitude of the plane is 2.4 kilometers, a flare is released. From the plane. The flare hits the target on the ground. What is the angle theta? Let's see, we'll put theta right here. All right, so it says an airplane is flying at a velocity of 240 meters per second at an angle of 30 degrees. All right, and so the airplane is actually directed downward. So you imagine what the horizontal is. It's at a 30-degree angle, and it's going 240 meters per second. I mean, again, I will draw this. And then it says it's gonna essentially release a flare. That's essentially it's gonna drop projectile when it has an altitude of 2.4 kilometers, and essentially it's going to hit the target on the ground. We want to find out what the there's a particular angle theta. It's actually called a line of. I'm going to reproduce a drawing. It's called a line of sight angle. We want to find out what that angle is. So again, kind of keep track of what this problem says, and now I will draw the picture that corresponds with it. Okay. So we have the words. Let me now draw the corresponding picture. Again, Cutnell Johnson 3.43. Okay, so the picture looks like the following. So we have essentially a location of an airplane. I'm just going to put a little dot. So here's the horizontal. It's flying with a velocity vector so it's flying at a v naught. So the airplane flies at a v naught. Okay. At an angle of 30 degrees from the horizontal. So this angle is 30 degrees. So you're essentially your theta naught, if you will, or call it your theta naught, equals 30 degrees. I mean, that's what the airplane is right now. And it's going to be when it releases its package or its flare, it is at an altitude of 2.4 kilometers. So we imagine, draw this a little bit better. So this airplane is at an altitude of 2.4 kilometers. All right, and here's the ground. Essentially, what's going to happen? Well, it's going to release a flare. Now, at this location, the flare, is kind of like the hot air balloon problem that we did in Chapter 2. The flare will have the same velocity as the airplane when it is first released. So this V naught is actually, now who knows what the airplane's going to do after this? But when the flare is released, it's going to have the same initial velocity vector as the airplane. And then it'll become a free fall particle, kind of like the coin thrown out of the hot air balloon, like last time. Here's kind of almost like a two-dimensional version of it. So what's going to happen here is that you're going to have this initial velocity vector V naught, and essentially the flare will follow. It'll follow a projectile. V naught out of the way here. Yeah, let's see, V naught. Okay. It'll follow a projectile motion. It's going to be in free fall. It's going to have some horizontal component of velocity that will not go away, and its vertical component of velocity will essentially increase. And so it's going to hit its target. Let's say here's the target, truck or tank or whatever it is. It's going to hit a target, and the picture that you don't see is a straight line, what we call a line of sight, between basically where the projectile or the flare was released to where it strikes. So let's see if I can try to draw this line of sight vector, or not, sorry, line of sight. There, it's not too bad. So again, that's not the path that the flare follows. This is the path that if you had an eyeball looking over here, you would look straight up to where the projectile actually is being released. The reality is the flare will actually follow this this projectile, this actual trajectory, what we call the parabolic trajectory, for free fall or for the projectile motion. All right, so we want to know what this angle theta is. That's what this problem wants to know. We also know this. We also know what we call y minus y naught. We know that y minus y naught is 2.4 kilometers. So essentially what we're going to need to know from this problem, and let's kind of think ahead. We have enough physics knowledge to figure out, how this trajectory is going to occur. But what we're really going to need, to actually figure out this theta, is we're going to need this other length, x minus x naught, which is the range. We're going to need to find that range. Let's kind of plan things out. Like, here's the plan of action that we need to take to solve this problem. We need to find that range. Because that range is, once we find that range, it's going to be a simple tangent function to figure out theta. All right, so that's what we need to do. And so to do that, essentially what information that we do have is we're going to need to gain information by looking at the free fall and then combining that with the range equation and coming up with the right way to determine this. All right, and so what do we know? Well, we know that there's going to be an initial component of velocity for the flare being fired. The component of velocity that remains constant, the horizontal component of velocity, we'll call that V naught sub x. All right, so V naught sub x is going to be, again, as I've said a few times, it's going to be V naught. V naught is the initial velocity vector of the projectile and then we have the adjacent. The x component is going to make an adjacent leg. So it'll be v naught cosine of theta naught. And in fact, we know what v naught is. We know the magnitude of v naught. We're told what that is. Or we'll say this is v naught here. We're told the magnitude of v naught in the problem. It's 240 meters per second. Okay, we're told this. This is a given. And so in that case, we actually can do this. We know that this is going to be v naught sub x will be 240 meters per second times the cosine of 30. All right, and so if you do that, you find that that's going to be 207.8 meters per second. So v naught sub x, we know what that is. We can calculate it right now. So v naught sub x is 207.8 meters per second. All right, so we know that. We also can figure out v naught sub y. Again, it's not going to be 0 because there is a vertical component. So v naught sub y in the same token, so again, this is an important piece of information. V naught sub y will be v naught sine of theta naught, or v naught sub y will be 240 meters per second times the sine of 30. Well, we know the sine of 30 is a half. So v naught sub y will be 120 meters per second. So we know the initial velocity vector of the flare. Okay, so we know what is, again, the component x, the component velocity is going to be constant throughout this entire problem until the trajectory strikes the ground. What's going to happen in the vertical direction is it's going to start off with a 120 meter per second trajectory, and then it's going to, there's going to be a gravitational acceleration down toward the ground, and this final velocity is going to be larger. Okay, and so essentially, well, we don't need to know the final velocity. We need to figure out, like, well, what do we need to know for this problem? Well, what we actually need to determine is, well, what do we know? We don't know anything about the final velocity in the vertical direction. We don't know anything there. We do know that y minus y naught is 2.4 kilometers. Okay, so we know that. So we know the vertical distance. We know the initial vertical velocity. We have no idea about the final vertical velocity. We don't know that yet. But again, what is it that I'm eventually after? Well, I'm eventually after, I know y minus y naught. I need x minus x naught. Well, let's see. If I could find x minus x naught if I knew how long this problem was going to last. Because it's a simple matter. It's a simple constant velocity motion in the x direction. X minus x naught is v naught sub x times the time. I know v naught sub x. If I knew how long this problem was going to take, if I knew the time, then I would be able to find x minus x naught and the problem's done. So the question is, I don't have enough information in the x direction to find the time. I have to use the information in the y direction to find the time. So, so I need to find time. So I have to pick an equation that's best to use for the information that I know. So I know that y minus y naught. All right, let's see, what equation could I use? Well, v naught sub y, t, and I'm going to consider an upside down positive y-axis. Because essentially this is a problem where all you have is falling going on, right? So you might as well just make an upside down y-axis since there is no upward motion. All right, so I will say plus 1/2 gt squared. I'd like to find t. I know y minus y naught, that's 2.4 kilometers. I know v naught sub y, that's 120 meters per second. I know g. So essentially, I have a quadratic equation to solve. If I solve the quadratic equation, so again, let me, again, I need real estate here, so let me try to note down what I have here. So let's say I know v naught, so I'm kind of pull in a corner here. I know v naught sub x, and I need more space. V naught sub x, let's just write down what I have determined so far. 207.8 meters per second. And I know v naught sub y. Let's write that over here too. And that's 120 meters per second. Okay, I just need to write down my results so far and erase. All right, and so let's do that. Let's erase this and let's try to solve. We have a quadratic to solve now. Let's now solve for the time. Okay, so here we go. Let's write the original equation. Y minus y naught is v naught sub y t plus 1/2 g t squared. That's the kinematic equation that I'm going to utilize. And again, I need to make this in the form of a quadratic. So probably the best thing for me to do is take the displacement and put it down on the other side. And I'll kind of rewrite this equation, put the right side on the left and the left side on the right. So I'm going to write this as 1/2 gt squared plus v naught sub y times t. And I'm going to say minus the y minus y naught. Okay, and that's equal to 0. And let's see if that, yep, that fits. All right, so what I've done is I just flipped about the equal sign. I put what's on the right on the left and what's on the left on the right, and then I just moved it over. So I just rearranged to form an equation that looks like a quadratic. Now remember what the quadratic formula is. You know, we're just going to, when we've seen it a few times already, I'm just going to use it now. So t, remember, negative b. So negative b, well, that my b in this case is v naught sub y, so negative v naught sub y plus or minus the square root of v naught sub y squared minus 4. A is 1/2 g. Too much space I have left. And then c is, now let's be careful here, it's negative y minus y naught. That means that negative is going to cause this sign to be a positive. Y minus y naught. Okay, take the square radical of all of that and divide that all by 2a. And a again is 1/2 g. Okay, now the rest of it's just employing the quadratic formula. So t is negative v naught sub y plus or minus the square root of v naught sub y squared. 4 divided by 2 is 2, so I'm going to have plus 2g times y minus y naught. And that's almost at the end of my camera here. Square root of all of that in a radical. And then division, I have 2 divided by 2 is just 1, so it's all divided by g. And I'm ready to solve, so I'm going to have to do a little erasing up here now. This is the final looking formula. So now let's plug in numbers. I have it down as far as I can go. It's not pretty, of course, but quadratic formulas rarely are. So t, okay, so what is my v naught sub y? Well, I figured it out. It is 120 meters per second. So let's see, I can maybe start writing it over here. Negative 120 meters per second. All right, plus or minus the square root of 120 meters per second squared run out of space here, plus, let me just leave off the units right now, so I have a little bit of a space challenge here. So negative 120 plus or minus the square root of 120 squared plus 2 times 9.80, and then y minus y naught, again, that's 2.4 kilometers or 2,400 meters. We need to express it in terms of meters. So again, 2.4 kilometers, 2.4 times 1,000 is 2,400. All right. And so let's see here. Radical all the way across, and I'm dividing by g. Divide by 9.80. Okay, so if I do everything right at SI, like I did, again, I don't have enough space to really write everything out nicely. So what that is in meters, everything has to be in basic SI units. You don't want to leave that in terms of kilometers. That's going to be wrong. You have to write everything in terms of meters, seconds, and kilograms. All right? Everything has to be in the base SI units. So when you do this, you work this radical out, you end up finding out that the total time is going to be let's see, it'll be negative 120 plus or minus this radical, if you work it out, becomes 247.9. And all this is divided by 9.80. So again, what you're going to see is that you have two solutions. The root that's positive, well, this negative 120 plus 247.9, that's going to be a positive value in the numerator. However, if you did the negative, you'd have a negative value. You know that the time cannot be negative. So discard negative roots. Okay? If you do that, you want to then do negative 120 plus 247.9 divided by 9.8. And when you do that, you'll find out that the time is 13.0 seconds. That's how much time that this projectile will be in the air. Great. Now that I have that time, it is a simple matter to find the range. At this point, then, the range, x minus x naught, simply becomes v naught sub x, which is always the same. Again, remember, the x component of velocity is always constant times t. X minus x naught will be the v naught sub x, which is 207.8 meters per second, multiplied by the time, which is 13 seconds. Okay, and we find out that x minus x naught is equal to 2,700 meters. Or another way of saying 2.7 kilometers. All right. Finally, we have what we need to answer the question. We were given y minus y naught. We finally found x minus x naught. So again, we had to find x minus x naught. Essentially, we needed the time. There wasn't enough information in the x direction to determine the time. So you had to use one of the equations, one of the kinematic equations in the y direction to determine the time. You had to solve a quadratic. Once you're able to solve the quadratic to determine the time, now is a very simple matter of using that constant velocity equation to determine what x minus x naught is. Now it's a matter of doing trigonometry. All right. So now we know what x minus x naught. We know y minus y naught. So now we're going to just do one more step. I'm going to erase this now and finalize the problem. I'm keeping my figure up so that I can show you what I'm doing. So what would the problem be? Well, it would be a tangent function, right? So again, tangent of theta is the opposite divided by the adjacent So tangent of theta is going to be y minus y naught, that's the opposite, divided by, that's the y direction displacement, divided by x minus x naught. And that's the x displacement. So, of course, we take the arctangent of both sides. We have the inverse tangent of y minus y naught over x minus x naught. Or the inverse tangent of 2.4 kilometers divided by 2.7 kilometers. Basically, what we were given divided by what we just determined. So, again, kilometers over kilometers cancel, as they should in a transitional function. All right, and so when you do all this, you finally determine that angle theta, that line of sight angle, again, this is the line of sight. That's what this is determined. It's called a line of sight. That line of sight angle, it's kind of a military term, is 41.6 degrees. And there you go. So again, this is a line of sight. They say that all the time in military terms. You hear that phrase all the time. This is a line of sight angle. All right. I'm gonna do. Let's see. Two more problems, and then I'm going to talk about one more concept real quick. All right, and finish up chapter 3. All right. So I'm going to erase this. All right, I'm going to do an OpenStax now. OpenStax 3.43. That one says, can a goalkeeper at her or his goal kick a soccer ball? Without the ball touching the ground. Or kick a soccer ball, I'm sorry, into the opponent's goal. Kick a soccer ball into the opponent's goal without the ball touching the ground. Okay, and it says distance will be about 95 meters. A goalkeeper can give the ball a speed of 30 meters per second. So again, what's the goalkeeper's capability? A goalkeeper when he or she kicks the ball, can give the ball a speed of 30 meters per second. Okay, so read it again here. Can a goalkeeper at his or her goal kick a soccer ball into the opponent's goal without the ball touching the ground? The distance will be about 95 meters. That would be the range. And a goalkeeper can give the ball a speed of 30 meters per second. So this is actually an application of the range equation. What we're asking is, we know the horizontal distance that the goalkeeper has to kick the ball. So horizontal distance of 95 meters, which we would call the range. And the goalkeeper has the ability, essentially this is the launch velocity of to employ a launch velocity to the soccer ball of 30 meters per second. Okay, so again, this is all the information we need to know to essentially use the range equation. All right, and so I'm going to erase this. And we're talking OpenStax 3.43 again. Okay, so what I know is that, let's just say the goalkeeper can kick the ball. I want to try to figure out if the ball can get to the opponent's goal. All right, so this R is 95 meters. And we know that the goalkeeper can employ initial velocity, and the magnitude of that velocity that the soccer ball, that would be imparted to the soccer ball, is 30 meters per second. This is the information that we know. All right, and so the question is, we want to try to find if the goalkeeper has the ability to do this. And so so essentially, what is the range equation? Let's start off with that. Remember, the range is V naught squared over G times the sine of 2 theta naught. Okay, and so we know what the range that has to be achieved. Gravity is constant, and we're given V naught. So the question is, when you're faced with a problem like this, there's a number of different ways to do it. The way I usually like to do it is to solve everything for the sine function. Okay, don't go trying to solve, do an inverse sine and have your calculator blow up. Kind of see if your sine function is giving numbers that are reasonable. And the answer would be that essentially, if you find out that when you calculate a sine function, that you get a value of less than 1, then it is possible. That means there is some sort of an angle at which the goalkeeper can kick the ball and make this happen. If you find out something like the sine function gives you a value greater than 1, that means it's impossible, because you can't have a sine. A sine of an angle cannot be greater than 1. The max it can be is 1. All right, so that's kind of the approach I want to take. I want to actually solve for the sine of theta, or sine of 2 theta. So sine of 2 theta sine 2 theta naught is going to equal what? G times R, I'm going to cross multiply, so GR divided by V naught squared. I'm going to cross multiply GR, and I'm going to divide by V naught squared and kind of flip the equation. All right? All right, so what I'm going to do now is say, okay, well, sine of 2 theta naught, what's it going to be? I have all the values that I need in the given. Let's see, G 9.80 meters per second squared. We're told that the range at which the soccer player needs to be able to kick the ball is 95 meters. And we're going to divide by the speed in which he or she can impart to the soccer ball is 30 meters per second. And I need to be sure to square that. When I work this all out, again, this is going to give me a unitless number on the right-hand side. When I work this all out, I will find out that the sine of 2 theta naught is going to equal about 1.03. There is no way that the sine of any angle can give you 1.03. The maximum value that a sine function can give you is 1.00. So this is impossible. This is nonsense. So essentially, the answer to this question is it's impossible. I mean, I'd write some other stuff, but basically the goalkeeper cannot do this, because we know that when we solve for the sine function, we have an impossible situation. We have a value that can never be achieved. So you see nonsense like that coming from an equation, that means that it's not doable. Okay? All right, so now I'm going to do one more problem, and I'm going to talk about essentially one more quick concept, and I'll call it a done deal on this video. All right, so I'm going to erase this. Okay, I'm going to do OpenStax 3.36. Okay, so this says it's the world long jump record. Is 8.95 meters. And that was done by Mike Powell. USA, 1991. Right? Treat it as a projectile. What is the maximum range attainable by a person? If he has a takeoff speed of 9.5 meters per second. Okay, so we basically know the muzzle velocity, if you will, or the launch velocity of this person. All right, so this person can essentially project himself as a projectile at a maximum velocity, basically at a velocity of 9.5 meters per second. I mean, that's as good as this person can do. The question is, if this person went all out and obtained that kind of velocity, could what would the max essentially what are we looking at? What maximum range can this person obtain? All right, so I'm going to erase the problem here. It's a fairly small problem, and so we go back to the range equation. And so we're told that essentially that V naught for such a person is 9.5 meters per second. Okay, so we go to the range equation. Okay, well, the range equation, I know that is V naught squared over G times the sine of 2 theta naught. Okay, so the maximum velocity this person can get is 9.5. G is a constant. So I have to figure out, and I said this earlier, I'm going to maximize my range. I do that if I can maximize my sine function. So I know that can happen. So sine of 2 theta naught is a maximum of 1.0 if theta naught equals 45 degrees. So if this person does everything perfectly, goes all out as far as getting the maximum velocity, basically launch velocity possible, and does it at a 45 degree angle, then this person can literally get the maximum range. So we would find out that R max would be V naught squared over G times basically 1. I mean, the sine function would be maximized out at 1 at 45 degrees. The sine of 90 is 1. So we see that this person has a maximum velocity of 9.5 meters per second, quantity squared, divided by G, 9.80 meters per second squared. We find out that the maximum range that such a person can obtain is 9.2 meters. All right, so that's pretty much the kind of day that Mike Powell had. So Mike Powell, even, I guess, if you think about this, he probably got his 45 degree angle. That means he can actually project even faster than 9.5 meters per second. Since he actually did better than this. No, actually, no, he didn't. He had 8.95. Okay, so I'm sorry. Yeah, so he had a day like this, right? Not quite as perfect. But, 9.2 meters. So I think his record was 8.95 meters. Anyway. So he had a day very similar to this. Okay, so that's it for the range equation and projectile motion. I want to talk about one last concept, and then that's it for this chapter. The last concept we want to talk about is what's called relative velocity. All right, and so the relative velocity, one of the things that we have to remind ourselves, and sometimes we forget this, it seems, that when you calculate a velocity, it is truly with respect to a reference frame. So for instance, we go to watch a Rangers game, and you'll hear about let's say the pitcher Yu Darvish throws a 95-mile-an-hour fastball, and that's all they say. Well, what they really ought to say is he throws a 95-mile-an-hour fastball with respect to the reference frame of Rangers, or of the stadium, whatever the stadium is called. It used to be called Ranger Stadium, but whatever it's called, with respect to the field, 95 miles per hour with respect to the field in a certain direction. But the announcer never says that. But we do know inherently that we do have a velocity with respect to a reference frame. I mean, even though we may not say it, we know it inherently. Now, I'll kind of tell you a little joke that a couple of my friends played on me to kind of give you an example of that. That this is intrinsically known to us. So, for instance, I went out with a couple of my friends. We're young in our 20s, and we had lunch together, and then we leave, and we're all at a stoplight. I'm in the middle lane, and I have a friend on each side. They decided to play a trick on me. They decided to coordinate with each other and slowly put their cars in reverse. Now there's nobody behind them, so they both were slowly putting their cars in reverse at the same time. And they thought it was hilarious to see my reaction. I grabbed my steering wheel and I jolted because I thought that I was actually rolling into the intersection. And I was just, and then they, again, I wasn't too pleased at the time, but it's funny. But essentially, why did I react that way? I reacted that way because I know that my velocity, I know inherently that my velocity is with respect to the ground. If I'm stopped, I don't expect anything to be moving. I mean, you have two cars, my friends, we're all at a stoplight. I don't expect them to be moving with respect to me. And all of a sudden, I see them moving with respect to me. Then I automatically assume that my car is moving. So I have an inherent understanding, and so do you, and so does everybody, that the velocity is with respect to a reference frame, whether we say it or not. Now, when we talk about relative velocities, we do need to be more specific about the reference frame that we're talking about. So I'm going to talk about, first of all, a simple example, and then I'll show you. Well, we'll finish up the video, and I'll go through an example of a two-dimensional example. A two-dimensional example of it. So, what is relative motion? This actually is a very, very important problem. This is, when you see the word relative, that's the same relative that's in relativity. This very problem is what Albert Einstein thought about when he devised the special theory of relativity. So in one dimension, it's pretty simple to understand. So you imagine, for instance, that if you're watching me, let's say we're in a classroom together, and I'm in front of you, and I throw a baseball. Let's say, I'm not you, Darvish. Let's say I throw a baseball at 70 miles per hour. So I'm throwing it, let's say, to your right in the classroom, and I'm throwing the baseball at 70 miles per hour. And you definitely would say, yes, you're throwing the baseball at 70 miles per hour to the right. No problem. We can agree on that. But let's say instead, you see me instead now is I'm on a big railroad flat car. So I'm on a car, big flat car, and here I am, and I'm going to throw the baseball. We'll say it's at 70 miles per hour. Now that's 70 miles per hour as measured by me with respect to the flat car, to the car. So again, we'll say that's 70 miles per hour that I would measure my baseball being thrown. However, I happen to be in a flat car that's going at, let's say, 80 miles per hour. Almost say, that'd be kind of scary. We'll say 50 miles per hour. Okay? And so you are watching this situation unfold. And let's say it's a fairly large flat car, and I am really going at a constant velocity. So essentially, I have no idea, unless I can see far enough, I have no idea that I'm even moving. Again, you never know if you're moving unless you accelerate. All right, and so as far as I understand, I'm perfectly at rest in my reference frame, and I'm throwing 70 miles per hour. You're watching me from afar, and you see that I happen to be on a platform moving to the right at 50 miles per hour. You're going to see the baseball going how fast? You're going to see the baseball going 70 miles per hour plus 50 miles per hour. You're going to see the baseball going at 120 miles per hour. So you will say in your reference frame, which is stationary to the classroom, that you see the baseball, or stationary to the ground, that you see the baseball going at 120 miles per hour. I will say, with respect to my reference frame, which is the railroad flat car, that no, I'm throwing the baseball at 70 miles per hour. Okay, so what calculation are we really doing? If we imagine that I want the velocity of the ball with respect, so I'm seeing what? I have the velocity of the ball, so let me kind of write this out. So velocity of the ball with respect, so let me hang on one second. Let me do some shorthand. I'll let B mean ball, okay? I'll let C indicate car, and I'll let E indicate earth, okay? So, what are we doing? Well, we know that the velocity of the ball with respect to the earth is equal to the velocity of the ball with respect to the car plus the velocity of the car with respect to the earth. All right? So the velocity of the ball with respect to the car, that's 70, plus the velocity of the car with respect to the stationary earth, that's 50. Those two added together give me the velocity of the ball with respect to the earth. Okay, so this is a basic vector addition equation. Now this vector addition is real simple in one dimension. Why? Because a direction is only a plus or minus sign in one dimension. So again, I have a platform. I call it the car, and then there's the ball. So the velocity of the ball with respect to the platform, the car, plus the velocity of the platform, and again that's 70 plus platform with respect to the Earth. That's equal to the velocity of the ball with respect to the Earth, which is what you see. What I see, if I'm not aware that I'm on a moving car, what I see is the velocity of the ball with respect to the car. That's why I'm going to disagree with you. I'm going to say it's 70, and you're going to say it's 120. We're both right. I just happen to not understand that I'm on this moving car. I'm giving you an answer with respect to my reference frame, and you're giving me an answer with respect to your reference frame. And so for those of you who take physics 2, we will study special relativity. We'll find out that you may have two observers who disagree, and yet they're both right. All right, and so this is called relative velocity. And you notice that I said velocity of the ball. Well, let me actually say it the way I should say it. The velocity of the ball relative to the car plus the velocity of the car relative to the Earth equals the velocity of the ball relative to the Earth. We really ought to use the word relative. I'm saying with respect to it. It means the same thing. So again, that's what we're doing here. But again, this is a vector addition. Now what I'm going to do is I'm going to work out, as the last thing we do tonight, or at least in this lecture, I'm going to work out a relative velocity problem in 2 dimensions to show you that in 2 dimensions it becomes a more difficult vector addition. All right, so let's keep this in mind, and I'm just going to work out a problem, and that's the last thing we're going to do. And it's going to be a relative velocity problem in 2 dimensions. And we're going to realize it's going to be a vector addition. All right, so I want to work out OpenStack's 3.66. Okay, so we'll work that out, and that's it for this lecture. All right. So it says a ship sailing in the Gulf Stream is heading 25 degrees west of north. I guess they say 25.0 degrees. Okay. At a speed of 4.00 meters per second. Relative to the water. Its velocity relative to the Earth is 4.80 meters per second. At 5.00 degrees west of north. What is the velocity of the Gulf Stream? Then it goes on to say, in parentheses, the velocity obtained is typical for the Gulf Stream a few hundred kilometers off the east coast of the United States. So again, this is the Gulf Stream. And so again, let me read this again one more time. A ship sailing in the Gulf Stream, let's kind of remember this, is heading 25 degrees west of north at a speed of 4.00 meters per second relative to the water. Okay, so basically the speed of the ship relative to the water, and its velocity relative to the Earth is 4.80 meters per second at 5.00 degrees west of north. What is the velocity of the Gulf Stream? Again, that's the water with respect to the Earth. So essentially we have the velocity of the ship with respect to the Earth, the velocity of the ship with respect to the water, velocity of water with respect to the Earth. So let's try to figure out what we have. So I'm going to erase this, and I'm going to draw a couple of vectors real quick. So again, two-dimensional vectors, and remember what we have. And this is OpenStax 3.66. Okay, so let's draw a couple of graphs. So what were we told? Well, we're told. Well, let's see here. What general equation are we're gonna talk about here? So we're gonna let S. When we say S, it's gonna represent ship. When I represent W, that's gonna represent water. And when I say E, that represents Earth. All right, so essentially my generalized equation in two dimensions is going to be the velocity of the ship relative to the Earth. Okay, again, I have the ship on top of the water, on top of the Earth. So I kind of have a multi-layered problem here. So velocity of the ship, so I always kind of think of this as layers. So I have the ship on the water, on the Earth. Okay, so again, I'm asking the velocity of the ship relative to the Earth is equal to the velocity of the ship relative to the water plus the velocity of the water relative to the Earth. Okay, so again, the velocity of the ship relative to the Earth is equal to the velocity of the ship relative to the water plus the velocity of the water relative to the Earth. What we actually want here is the velocity of the Gulf Stream. That's the velocity of the water with respect to the Earth. All right? And so what are we told? Well, we're told that, let's kind of draw the graphs out of what we're given. We're given, again, what I like to do, even though we're being told, we have north, south, east, and west, I like to translate that into an XY coordinate for the moment, and then we can always convert it back later. So I like to think in terms of plus x, plus y, and minus y. And what are we told? We're told that we have 25 degrees west of north, for the velocity of the ship with respect to the water. So if you read this carefully, the velocity of the ship with respect to the water is at 25 degrees west of north. West of north. So this angle is 25 degrees. Okay? We're also told about the velocity of the ship with respect to the Earth. And we're also told that's also west of north, but that's only 5 degrees. So velocity of the ship relative to the Earth. And that's at 5 degrees. And again, north, south, east, west, or what I prefer is plus x, plus y, minus y. So again, those are the two vectors that I have. What I actually need to do at this point is I need to break them into their components. Well, first of all, I need to do a little algebra here. Then we have to break the vectors into their components, and I got to figure out what the final vector is. So I'm looking for velocity of the water respect to the Earth. So what I got to do is I basically have to subtract velocity of the ship with respect to the water from both sides. So I rewrite the equation as the velocity of the water with respect to the Earth is going to equal the velocity of the ship with respect to the Earth minus the velocity of the ship with respect to the water. I mean, all I've done is I've subtracted, all right? And so this is the equation that I really want to look at, all right? So what we have to do is, I would say we need to just remember these two graphs because, I mean, honestly, if I had enough whiteboard space, I'd leave them drawn, but we need to, we need to conserve space here. So the important equation that I want to remember is this one so far, and we're actually keep note of these two plots. I'm going to have to erase everything except the equation. So again, this is the limitations of my whiteboard. So again, we'll just have, I hope you're taking good notes with me. All right, so we have our nomenclature. I have the original equation and the equation which we're going to try to solve. So again, the equation that I really care about is this one. So I'll put it up. I guess I'll put it up here. The velocity of let's see, the velocity of the water with respect to the Earth is the velocity of the ship with respect to the Earth minus the velocity of the ship with respect to the water. Okay, that's the equation I want. So, looking at the first one, I want the velocity of the ship with respect to the water. Okay, so remember that equation was at a 25-degree angle west of north. So actually, let me just kind of draw it out briefly. So let's remind ourselves over here what that looked like. So again, I have plus x minus x plus y minus y. And again, I have an equation looks, basically, this is the velocity of the ship with respect to the water. Okay, again, this is a 25-degree angle. I need to break this vector into its components. All right, and so again, this is the angle that I have. And so the x component this time is not going to be a cosine like it normally is. Now the x component is going to be a sine. All right, the x component is now, the way this angle is drawn out, the x component is actually going to be the opposite. It's actually going to be the sine. And the y component, that's the adjacent. All right, and so again, this is going to be a little different than you're used to. And so now the x component is going to be negative, and the y component is going to be positive. The way this, it's a second quadrant function. So again, we're going to do a couple things at once. So I'm going to say that the velocity of the ship with respect to the water is sub x, v sub SW sub x. I need to calculate these components. So v sub SW sub x, again, this component, so I don't put a hat on, so it's x component. It is going to be negative, despite its very definition being in the second quadrant. Negative v sub SW sine of 25 degrees. All right. Again, as I said, it's a little odd because the way I've been doing things, we always have the x component being a cosine. Remember, the x component is in the direction of x. That's this direction right here, which is going to be the opposite of this angle. All right, so let's work this out. V sub SW sub x is going to be negative, and I'm being told that that value in the given is 4.00 meters per second. Times the sine of 25 degrees. Okay, so I work this out. V sub SW sub x then becomes negative 1.69 meters per second. Okay, that's the x component of V sub SW. I need to get V sub SW sub y. That's going to be positive by its very definition. It's a second quadrant vector. So again, V sub SW sub y will be positive V sub SW cosine of 25 degrees. So V sub SW sub y will be positive 4.00 meters per second times the cosine of 25 degrees. I find that V sub SW sub y, if I work this out, it becomes positive 3.63 meters per second. great. I have the components of V sub SW. So what I should probably just do is grab them and kind of put them in a little parking lot. So actually, I can probably just stick them over here for now. Let's see, let's park this. So V sub SW sub X. Let's see, I'll probably run out of space here too. All right, V sub SW sub X. I'm going to write that over as, again, let's be careful, negative 1.69 meters per second. And V sub SW sub Y will be positive 3.63 meters per second. All right, and yes, we're still, well, barely. Okay, so that's the results that I have. And I got to work out the SE. So now I'm going to erase all the stuff for SW, shift with respect to the water. And now I need to do the other vector. So I have the results that I need. I just wrote them out there. That's what's important. All right, and I need the V sub SE. So that vector is going to be 5 degrees for V sub SE. That's the shift with respect to the Earth. Okay, so that one's going to be 5 degrees. And so, again, it's going to have the same kind of components. So V sub SE sub X will be, again, it's because it's a second quadrant vector, it's going to be negative as well. Negative V sub SE. And again, the same kind of deal. It's going to be the sine of 5 degrees. Okay, and V sub SE sub X will be negative, and what was that? It was a 4.8. Times the sine of 5 degrees. And I find out that V sub SE sub X will be negative 0.42 meters per second. All right? And V sub SE sub Y, and that's going to be the cosine now, and it's going to be positive. It's the second quadrant vector, so positive. V sub SE cosine of 5 degrees. So V sub SE sub Y is going to be positive 4.80 meters per second times the cosine of 5 degrees. V sub SE sub Y will then be positive 4.78 meters per second. All right, so what I now have is everything that I need. I've calculated the components, so let's kind of now we'll see if we can try to collect these other ones here. So what did I say? V sub SE sub X is negative 0.42 meters per second. All right, and then V sub SE sub Y, okay, and that's going to be positive 4.78 meters per second. All right, so that's the results. All right, so now what I need to do is I need to put everything together to find information about V sub WE. All right, and so if we know V sub WE, it's V sub SE minus V sub SW, as I just got done saying. All right, and so V sub WE, well, it's going to be V sub SE. Well, what's that going to be? Well, V sub SE is this. X component, negative 0.42. I'm going to not worry about the meters per second right now. X hat, again, in the X direction, plus 4.78 Y hat. Okay, so that's just stating the vector. Here's where it gets tricky, is I'm now subtracting the other vector. Well, I'm just going to state the vector first. So again, I got to subtract V sub SW now. So negative 1.69 X hat, and then this is positive 3.63 Y hat. And of course, we know that everything is in terms of meters per second. Okay, want to kind of pop the unit on there. All right, so now what has to happen is, remember, when I subtract, I'm really adding the opposite. I'm gonna really add. I'm gonna distribute this minus sign through here and turn this into an addition. And so V sub WE will be negative 0.42 X hat plus 4.78 Y hat plus, I'm distributing the negative sign. This becomes positive, this becomes negative. So positive 1.69 X hat minus 3.63 Y hat. All right. And then what I'm really able to do at this point is I'm just going to erase maybe this line here. So I'm going to combine like terms at this point. So I'll combine my X hats. So I have V sub WE. Okay, so it's going to be negative 0.42 plus 1.69 X hat plus, what do we have? 4.78 minus 3.63 Y hat. Okay, and then one more little bit of arithmetic, and we'll get, you double check the math here. Yep, that's right, and then yeah, that's right. All right, I'm sure I didn't mess anything up. All right, so V sub WE. So I'm going to erase this equation. And so it's really just a matter of doing arithmetic on each of the components. So V sub WE. So 1.69 minus 0.42, that becomes positive 1.27 X hat. And then 1.69 minus 3.63, that's, I'm sorry, 4.78 minus 3.63, that's going to be positive 1.15 Y hat. So again, negative 0.42 plus 1.69 is 1.27 X hat. 4.78 minus 3.63 is 1.15 Y hat. So what we actually have, it's interestingly enough, is that even though V sub SW and V sub SE were both second quadrant vectors, when I perform this arithmetic, the Gulf Stream, we find out V sub WE, the velocity of the water with respect to the Earth, is actually a first quadrant vector because we see that it has a positive X component and a positive Y component. So it's actually a first quadrant vector. We can determine that right now. All right, so I'm going to erase the stuff on the right. I don't need this any longer. I use the components for what they're worth. Now we're just talking about the velocity of the water with respect to the Earth, which is the velocity of the Gulf Stream. And so what we need to do now is basically reading off this vector, knowing it has both positive x hat and positive y hat components. We know that the vector is going to be a first quadrant vector. So it's in the first quadrant. This look too good. Again. All right. So that is V sub WE. Okay. And I will determine, let's say, I'll use this as my angle theta. And I will get the components. And I do know the components. I know V sub WEX. And I know V sub WEY. All right. And maybe I ought to make this a little smaller. Do this again. So again, V sub WE, first quadrant vector. I want to determine theta. This is V sub WEY. And this is V sub WEX. All right. And so I need to use the usual way of using Pythagorean theorem and the inverse tangent to finalize this answer. All right. And so I want to find V sub WE, the magnitude of it. Okay. It's going to be the square root of 1.27 squared. Again, this answer is in meters per second. 1.27 squared plus 1.15 squared, square root of all that. I find that the magnitude of V sub WE, when I do this, is going to be 1.71 meters per second. Okay, that's the magnitude of the Gulf Stream. I need to find the angle. All right, so the angle, well, again, I've done this a few times. It's going to be inverse tangent of the opposite over the adjacent, or theta is the inverse tangent of W sub E sub Y, or sorry, V sub W E sub Y, the opposite, divided by V sub W E sub X. All right, and that's going to be theta is the inverse tangent of, and what's that going to be? Well, we find that V sub WEY is 1.15 meters per second, or 1.15 divided by 1.27. Let's write this neater. I end up finding out that theta is equal to 42.2 degrees. All right, so this was a long, complicated calculation, and it really was nothing more than a vector subtraction. All right, so my final answer, I'm just going to write my final answer now, so I'm going to erase some of this stuff now. And, you know, the final answer that you'd want to turn into me, if you did this problem, would be that V sub WE, basically the velocity of the water with respect to the Earth, is 1.71 meters per second at 42.2 degrees. What? It'll be north of east. Spoken in the same language what the problem was given. That would be the final answer. Okay? So again, this end up being a relative velocity problem, but it ended up being a vector subtraction. That's what it was in the end. So again, you know, noticing that the relative velocity problems are typically fairly involved in the calculations. I mean, well, they're as involved as a vector subtraction is, and so it's one of those things that you say it's involved, but the reality is this is a typical vector subtraction problem. And as we see, we are fully enveloped in the language of two-dimensional vectors when we're talking about two-dimensional physics, particularly when we're talking about a two-dimensional example of a relative velocity problem. And with that said, that is all that I have to say for chapter 3.